The fourth topic of this course is the serial communication. We already have used the USB UART bridge of the KitProc, which actually communicates with this PSoC5 target processor via the standard UART port or bidirectional UART port. And in addition to that, actually now we are in this exercise and this topic we are going through some sensor interfaces, typical sensor interfaces. So let's start again this slideshow. I have a slideshow, surprise. Okay, and full page, that looks good. Okay, so first of all, the serial lines, two kinds. It can be asynchronous or synchronous serial communication, no matter what kind of type it uses. The synchronous mode actually requires that we have a let's take the pointer again, so that we have a data line and clock line as on the data bus. So basically the clock line is used to time the data correctly, which means that this receiving end or transmitting end doesn't need the synchronization itself, as long as someone is controlling the bus and running the clock there. The other one, which is more common, is asynchronous clock line, and as you can see, it uses half the physical resources, and that's why most of the lines are asynchronous. So practically we have only the data line, which basically has some specific speed, which is agreed on both the sending and receiving side. So, and some protocol which is also known, and then basically everything is based on strictly on the local timing, so local synchronization on a device on both ends. Okay, so UART, universal asynchronous receive and transmit. That's where the acronym actually comes from. And actually it's a peripheral function which does serial data transfer independently from any other functions or devices. The PSoC actually has modules for serial transmitter receiver as well as UART, and you already have used this UART line. If you connect this PSoC5LP, the board, the transmit and receive lines to 12.6 and 12.7, then they are connected internally also to the KitProc programmer, and the KitProc programmer is just transparently that transfers whatever data is coming there to the USB virtual port in the computer. And of course it has really nice receive buffers, or actually there is some old information I think here. I need to at some point update that one. So there is a variable length transmit and receive buffer, first in first out buffers, and API functions to totally control the line wherever you need it. And basically for running the UART you just need to configure it correctly. And datasheet of course has more information how to and you have already done the you already have done the parameterization of this UART component. When we are talking about UART, it's basically also good to talk about this RS-232, which is old-fashioned, old-school serial line, or actually currently it's Electronics Industry Association norm 232, and that's currently what it shows on the what is the logic levels and that kind of thing. So data signals, transmit and receive data, and ground are required. That's the simplest form of a 232 bus. But there are also handshaking signals, which comes from the era of modems. So 30 years ago, modems were still used, standard modems with funny noises. So, for example, there is the ring indicator signal that tells the computer side that, okay, now there is a incoming data call to the phone line, and so on. And then there are also these handshaking signals to basically time the data correctly so that nothing gets lost. Voltage levels, inverted, logical 1 or idle is actually a negative voltage, and logical 0 is positive voltage. Okay, and as you can see, this is not even TTL compatible, although most of the modern AR232 these bus drivers actually do work also on TTL level signals. Okay, uses D connector, 9-pin or 25-pin. Most of the devices I have seen have been on these 9-pin devices, well, since 90s. Before 90s they were actually always that 25-pin. Then if it's a male connector, then it's data the terminal equipment kind of system, or if it's female, then it's data circuit ending device. So female connector practically means that it works like a modem, and if it's a male connector, then it works as a computer. Okay, most common framing. Okay, that's also old school. But anyways, if you need to guess a device which has a serial port connection, you would have no information about it. You actually can start testing it with different bit rates, and 9600 is the most common bit rate. Also 8 bits is the most common byte length. No parity is also common, and 1 stop bit. Connecting devices. Okay, if you have 2 data terminal equipment devices, then you basically just cross the wires. Of course, if you have for example, microcontroller on both of those, then the first microcontroller transmit must be the second microcontroller receive, and vice versa. And of course, both devices must have exactly the same parameters. So bit rate, number of bits, parity check, number of stop bits, which means pause between data transfer. Okay, virtual COM port. That's your most common the touch to these old-fashioned COM port utilities. So modern PCs, laptops, they have they don't have any these 9-pin D connectors anymore, or if they are not used for the serial line. So it's the serial port has become obsolete because of the cumbersome wires. They have big connectors and basically only single use and slow data transmission compared to USB. USB has basically replaced the serial port, serial lines everywhere. But anyways, this protocol has not gone anywhere. For example, it's common between these processors on single printed circuit board, so that they would actually use the COM or UART for the data transmission. It's still valid protocol, not just not between the these big devices and computers anymore, except of course if you have an old device. Okay, so but anyways, the COM port you have already used, so it's the same as if you go to the device manager and you have a device there, COM port. There's a COM4 there with a port. Okay, there's the COM port on my kit proc and port settings, something like that. Okay, yeah, there we go. Okay, so let's talk a little bit of the serial buses. This UART-based signaling is actually serial line. It's not really a bus. We can start calling a line as a bus if you have multiple devices in that bus. So in this illustration we might have several sensors on a black box, which is the PSoC device here, and then it communicates to the PC. I2C is actually acronym for Integrated Circuit and originally developed by Philips. So, well, Philips is not there anymore. It changed their name. It's still the same company, but anyways, they still hold the I2C trademarks, but that's the reason why some sensor manufacturers call it two-wire interface, and practically they are talking about the same thing. Exactly the same protocol, exactly the same speeds, or typical data rates, and yes, so okay, that's just naming convention. It's synchronous bus, meaning it uses, well, at least two wires, in this case exactly two wires. One is the data wire and another one is the clock wire. Both wires actually require one pull-up resistor, 4.7 kilo ohms or so, up to 1 meter of bus length, meaning that basically this is integrated circuits. So if you have devices on different circuit boards, then you basically need to have those inside of one single box. Practically, it's not for long data transfer at all. Okay, bus actually has single master and multiple slaves. There are also extensions to the protocol that you may have multiple masters, but then when one master is on the bus, then the other one is acting as a slave. Okay. and then you have basically some token that you will send from one master to another one so that the other master can take over. Okay, each device has 7-bit address. There is also extended 11-bit addressing mode. Master initiates all data transfer, meaning it basically sets the clock and data accordingly. For example, like that, how to transfer 1 byte. So practically, here's the start statement when the notice the clock and data, actually there's an offset on the picture. So clock is on the top and data is on the bottom line. And when you have clock is high and data goes low, that's the start condition. The opposite, meaning that when the clock is high and the data goes from low to high, that means stop. Otherwise, the data cannot change when the clock is high. So it can change the value only when the clock is low, just like here. So that is the start. Then the next following 7 bits are address byte. Okay, that is set by the master, sets the address, in this case 1, then changes state here when the clock is low, continues here 1001, and then basically there are some address bits here for the device, for example DS1621 device, and then sets write mode. This acknowledgement means that if there is a device with this basic address, during the next clock cycle or before the next clock cycle, that device must pull down the line, the data line. So basically asserting the acknowledgement. Next, the master then writes a command byte, which is just 8 byte the 8-bit data, and then again that device must acknowledge it and then stop. So basically, if you don't have a device, or if you don't have a device with that address, particular address, you don't get acknowledgement and here, and you can stop the transmission. Same thing here. Okay, very simple. Read and write. Okay, this is something you will be using on the exercise. Observe how to do transmit and receive of 1 byte. So first start sequence, then address and write, waiting for acknowledgement or reading the acknowledgement, setting the command byte, and getting the acknowledgement. Here repeated start. You must actually then, if you after write transmission, you actually get read transmission, then that you must first then make a repeated start, which means that the devices will be waiting for the address, and if it's the same address, same address but with read bit. So this 8th bit here, last bit on the transmission, if it's low then it's write, if it's high then it's read. So basically leaving it high then makes this device to know, now the master actually wants to read something, and acknowledges that one, and during the next 8 bits basically the device gives the data byte out. Okay, there might be more than one data byte, so if that is the case, you just continue with the acknowledgement. But if you want to stop the transmission, it was just 1 byte, then you say this master puts not acknowledged, so it leaves the this data line up in purpose. Okay, and then stop condition for the bus. Okay, remember this one when you are reading the data from the device what we are using. So it basically requires the address, correct address, checking that the acknowledgement is okay, setting the command byte, checking acknowledgement, then repeated start on the I2C bus, followed by the address again, but with the read bit on, then reading the data byte. But there are a application programming interface for this, so it's not that hard as it looks like. Okay, some samples. TC74, that's our device, and it looks like that. 5-pin TO something, TO5. Anyways, so it's a 5-pin device what you have on your kit, and that has actually that model has both SPI and I2C bus. In this exercise, you will be using the I2C bus. Then there are some other devices like 3-axis accelerometer sensor, color sensor, real-time clocks. Yeah, real-time clocks and so on and so on. And then of course this DS1621 temperature sensor. That might actually be better, so better device for this exercise. But anyways, you have this. You have the TC74. Okay, so it's a device with 7-bit I2C address, and this 3 bits actually can be selected using these 3 lines here. If you ground them, then the last 3 bits in address will be 000, or well, you can also put them somewhere, you know, some of them on 1 or so, what to choose, so you can actually hook up to 8 different sensors or 8 separate sensors of this type on the same bus without any other fancier type of the multiplexing. Yeah, and then it also includes a thermostat, so you can program it, and after programming, this T outline can drive something like, for example, a fan or heater or whatever to keep the temperature stable. Okay, SM bus, yes, there is SM bus, and that's actually one way of communicating with a battery. So laptop batteries, smart chargers. Okay, that's how you actually do these things. So how to manage power control and simple measurement tasks, or how to make it so that you cannot use anyone else's laptop battery but the brand. Okay, but now you know it, and now you can hack it. Yeah, PSoC5 and I2C. on PSoC, actually there are practically 3 different approaches to interfacing I2C. There are I2C master or multi-master or slave. You select it from the component, either using fixed or UDB. On fixed, it uses fixed I2C hardware, but the pin still can be selected freely. Good choice if only one I2C bus is needed. If you have multiple needs for I2C buses, then I would go with the UDB component, but anyways, it works the same. It just takes these UDB resources. But as I said, if only one I2C bus, then the fixed component, it leaves more resources for the other UDB components. Okay, then there's also slave mode, easy I2C slave, which is hardware implementation. Okay, but actually if you need to use this PSoC circuit as I2C device, slave, then this is a good choice. Yes, basically this provides you an easy to use interface to a memory area. Practically it's a part of EEPROM, so after programming also the I2C slave stays alive, and basically you can then read or write data from a I2C master processor and have the data transfer from for example the data acquisition system, what you already have here, have that data available for other processors using I2C bus. That's just an idea. Okay, some interfaces, but okay, I think you better just take a look at these. Look at these API functions on this on datasheet. But anyways, this more or less is the write read. So write read on a the bus, I2C bus. So basically this is the same as we saw here, more or less. So we have the starting, setting data on write mode and a command byte, then repeated start and write the bus again with the read signal, and then reading the data from the device. So this actually does it. So master send start to that I2C address with write bit. Then next one you will write this data byte to on the bus. Then you would send restart and then get the data using the master read byte and actually the read byte and acknowledgement, and then this I2C master send stop. Okay, so that will be doing that writing a command to read data from a device. Okay, so that was the I2C bus. Maybe I should actually make this into and tell you more about the SPI on different video.